Hi everyone, I'm Steve Sloan and I did my project on semi-definite programming for fair dynamic watermarking. Before I get too in-depth into things, I'd like to talk a little bit more about the problem setting. So we have the following linear control system where x evolves according to a linear process, and we see yn, which is a low rank version of x, all with some noise terms. One concern of this is that there's an attacker adding a vn term that skews what we see. One solution to detecting if we're being attacked or not is to add a small term, epsilon sub n, to the optimal control input un. Given that we know epsilon n and its covariance, we can do an analysis of yn to determine if we are being attacked or not. One test that we use this watermarking in is to calculate the following likelihood equation that you see there, and all of the matrices and parameters we can pretty much get from the system. So below I've shown a graph of what using this test typically looks like. We can see on the bottom we have the unattacked, it's very stable, very low, whereas we're being unattacked we see far higher values. So in this case, if we see large values for this test, we'll know that we're being attacked. Unfortunately, this test has one problem, and it's that we don't actually know the exact covariance of sensor or measurement noise. We can see in the test that these following two matrices, sigma delta and sigma sub z, both use the covariance of measurement noise. We have to approximate both these values, so we don't know if we've actually gotten the correct thing or not. This non-robustness can cause some serious problems if the actual noise is a lot further from what we think it is. So we can see the following two graphs. One time, the test is run when we guess the correct measurement noise. The other, we have the exact same parameters, the same measurement noise guess. However, the real measurement noise is different from what we expect. As we can see in the case where the measurement noise is different from what we expect, it is very difficult to distinguish between the unattacked and attacked cases. In fact, the two have almost the exact same distribution. This brings us to our more robust test and the semi-definite programs that I will be studying. So the problem is we want to design a test that's robust to changes in measurement noise. And in fact, we can design a test that is indifferent to measurement noises within a given range. We let omega denote a polyhedron of all measurement noises, and we can derive sigma k from the boundary points of omega. We can then use the sigma k in the following semi-definite program tests as we see below. Now, there are two cases for what the measurement noise could be. First, it could be fixed but unknown within a certain range. Or it could also be variant, so constantly changing throughout the duration of our test, but known within a given range. As we can see, the objective function that we have is a combination of the trace of the product of two matrices and then a log determinant and a constant. In our case, we are minimizing over the matrix V and the vector theta. These semi-definite programs can be pretty easily solved in MOSEC. There are a few problems that came up, but I'll talk more about those later. We can see in the graphs below that the test is very effective. The two graphs here show the test on the fixed but unknown covariance. In the top graph, we have our old test. We can see that it is unable to distinguish between the unattacked and attacked cases. The lower graph has the exact same true values for everything, but with our new test. We can see that in this case it can clearly distinguish between the unattacked and attacked cases. This slide shows the graphs in the varying covariance case. It looks pretty similar to the fixed but unknown case. In the top, we can see that our old test still was unable to distinguish. It started correct, but then as covariance moved away from what we thought it was, the test became useless. The bottom shows our new semi-definite program test. We can see that it maintained its effectiveness throughout the whole duration of the process, regardless of what the true covariance was. Before I attempted to use an algorithm to solve the semi-definite programs I showed earlier, I wanted to solve a slightly more simplified case. We remembered that our objective was to minimize this likelihood, which is the constant times the log determinant of a fixed matrix, which in itself is a constant because Sn is fixed, plus the trace of our decision matrix times, again, a fixed matrix, minus a constant times the log determinant of our decision matrix. We know since Sn is fixed, we can effectively simplify this objective to minimizing over some matrix that's semi-definite, the trace of ctx minus L times log determinant of x. We can see that I dropped the thetas, and I'm also going to consider more simplified constraints. I'm going to instead consider the more typical constraints we see in semidefinite programs, which are trace aitx equals bi for I equals 1 to m, and that x is positive semidefinite. I decided to solve this more simplified problem using the algorithm described in our textbook. Typically, algorithms that solve semidefinite programs solve the logarithmic barrier function as follows. We can see below that we have a log determinant in our objective in the log barrier function. Normally, we would like to find a beta approximate solution to this, and then move theta towards 0 to get to our linear objective. Luckily, in our case, we already have a log determinant case in it, so we can just set theta equals to L and get an exact objective without having to reduce theta at all. This means that our objective function is actually easier because it has a log determinant function and works very well with the interior point methods that I'm going to be using. In fact, our textbook, as a pre-processing step, gives a method to go from a strictly feasible starting point with a given theta value to a beta approximate solution with the same theta value. We can use this algorithm, but instead of just stopping when we get to a beta approximation and then start reducing theta, we will just completely solve the problem and go even further, and reduce beta even more. We arrive at the following algorithm. Initialize theta 0 equals to L, and some feasible x0. We then set x bar equal to xk and factor x into its following square root matrices. Then we have to solve the following Newton equations for the matrix d prime and the vector u prime. When I was coding this, I had to turn the entire Newton equations into one objective solving for a long vector, so I effectively had to vectorize d in order to solve it without a more sophisticated linear algebra solver. I just ended up doing a matrix inversion. We'll cut this out. Next, we update s prime. Next, we effectively check what beta value we are at. If we are less than a fourth, we set alpha equal to 1. Typically in this case, we would start reducing theta. However, in our case, we don't want to reduce theta, we want to keep it where it is, so we're just going to set alpha equals 1, which you'd normally do in subsequent steps. This effectively speeds up our conversion process because we can take larger steps because we know we're in a range where Newton's method will converge more quickly. In the case where this norm is greater than a fourth, we will set alpha equal to the equation shown, and then update x prime. Our next step is to set xk plus 1 to x prime, k to k plus 1, and go back to step 1. I chose to terminate when the norm shown was sufficiently small. I decided to test my algorithm with some random input matrices. I decided to do C as follows. I had two AIs, A1 and A2, which I've given, and then two Bs, which I've given. In part, I chose these numbers randomly, but I also chose them so I could have the identity matrix as a strictly feasible solution, just so I'd have a point where I could start. We can then run the algorithm and we find that we converge upon a solution. I checked the solution with a MOSEC coding of the code and got the exact same thing. In fact, when I ran my algorithm for 100 iterations, it took 1.4 seconds, compared with 4.9 seconds for MOSEC. I don't know how much of this had to do with me knowing a strictly feasible point at the start, but we can still see that mine was about 3 times faster than MOSEC. This has pretty strong implications for the practicality of our algorithm in our problem setting. One problem I had when I was using MOSEC to solve the original problem was that it took a very long time to solve. If you were trying to practically implement this in a control setting, you wouldn't know you were being attacked until it was too late because the semi-definite program was taking too long to solve. We can now look at some of the convergence results. We can see that while beta is greater than 1, we have pretty slow convergence. Beta decreases linearly, but at a fairly slow rate. However, as soon as beta gets under 1, we get in the zone of quadratic conversion. We can see there that the log beta graph sort of looks like an inverse parabola and declines very, very quickly. I've now given some of the following steps I would like to look at. First, I'm going to try to adapt the algorithm and modify the semi-definite programs I showed earlier so that we can actually have the algorithm work on them. We will have to try to move around some things so that they work with these slightly different constraints. I'm also considering looking at the semi-definite program algorithm suggested in the following paper and checking its runtime and convergence results against the other one. Thank you for watching. I hope you enjoyed my presentation.